So there are two ways that we can think about this. One is using a property of logs, and another is using a property of derivatives. I think I'm going to explain it using properties of derivatives because that's a good review for us. Notice that this is an outer function is natural log, and the inner function is 13x. So when I take the derivative of this, I have to use chain rule, where I think of the outer function as the natural log function. So the derivative of the outside function is the derivative of natural log, which is 1 over this function, 13x, times the derivative of the inside function, and in this case the inside function is 13x. So the derivative of 13x is just 13 dx. And notice that that means that these 13's actually cancel with one another, and we're left with just 1 over x dx. And if you wanted to, well, I'll just leave it like that, because there's no reason for you to have to review log properties that you may or may not remember. Again, this is fortunate because we actually have a 1 over x lurking in this problem. I can rewrite my original integral as 1 over x times the sine of the natural log of 13x dx. And that means that the 1 over x piece and the dx piece become my du, and this becomes the integral of the sine of u du. I'm going to go ahead and integrate this. The derivative of sine is cosine, so that means that the integral of sine is negative cosine of u plus c. But I don't want to leave it in this final form with a u. I want to go ahead and plug in my original u to get negative cosine of the natural log of 13x plus c. And the final problem that I want to talk about is number 13. And again, it's difficult to see which one of these pieces I want to be my u sub. One thing that I do sometimes when dealing with trig functions is I rewrite this as the tangent squared and secant of theta squared d theta. So how am I going to figure out which u to use? One thing that you can notice is that when I take whatever my u is equal to, the derivative of that has to be lurking somewhere in the problem. And we have memorized now that the derivative of tangent is secant squared. So if I let my u be equal to tangent of theta, then my du is going to be the derivative of tangent, which is secant squared theta d theta. And that's exactly this end piece. So it's a direct substitution in this case. So that means that it's easy for me to be able to say, aha, I'm going to plug in u is equal to the tangent theta squared. So that becomes u squared, and this whole piece becomes my du. Now I can do my easy integration. Don't forget my integration step. When I integrate this, I end up with 1/3 u to the third plus c. And then I plug back in, well, what is my u? Tangent theta. So I have 1/3 of tangent theta to the third plus c. And this question asked for one final step. They wanted to graph this function to verify our work. The easiest way to do that is to graph it either on GeoGebra or using a calculator. So I'm going to go in and I'm going to graph the original function, which was tangent of theta, our x value, squared, times, maybe this is the problem, that how do we type in secant squared into our calculator? Your calculator might not have a secant button, right? So what is secant? Secant is just the reciprocal of cosine. So I'm going to type in 1 over cosine of x in parentheses. I'm going to square that. And when I graph that, oops, my zoom is set to a funny window, but it's graphing it. Maybe instead of watching all that. let's go ahead and graph both functions, because we're going to have to graph both functions. Let's go ahead and graph our antiderivative for our integral here is 1/3, so I'm going to type in 1/3 tangent cubed tangent of x raised to the third, and we're supposed to take our c value equal to 0. So now it's thinking and graphing, and if I zoom in on the center, it should look similar to what you have for options. So I'm going to go zoom, standard, and now this picture is going to look similar to what your pictures would look like on the various graphing options. So this wiggly one is our original function, tangent squared secant squared. We know that because it takes on only positive values, which makes sense because both of these are squared, so they have to be positive. And then this one that has the cubic action has both negative and positive values. So this is a lonely group office hour. It's section 5.5. We're going to start by looking at number 2. All of these are u-subs problems. The first problem that we're looking at, the way that I have it written, it's the integral of x cubed times 3 plus x to the 4th, all raised to the 4th. And they give us a hint that our u-sub can be 3 plus x to the 4th. I want to back up for a second and say that it is possible to solve this just by distributing this all out. I could take this polynomial and raise it to the 4th power and then multiply it by x cubed, and I would get a really, really long polynomial, and then I could apply power rule to it. But a u substitution makes this much, much faster. The reason we can see that the inside function in this case is what we want to use our u for, because this chunk is raised to the 4th power, and if we let this be u, then our du is the derivative of this, which is 4x cubed dx. And we have an x cubed, which is great. There are a couple of ways to approach this. The way that I'm going to approach it is by multiplying a 4 and a 1/4 in this integral. Namely, this is the same thing as the integral of 1/4 times 4 times x cubed times 3 plus x to the 4th, all raised to the 4th dx. And I can do that because that's just multiplying by 1. And that means that this chunk, my 4x cubed chunk, and the dx chunk can become my du. And I can rewrite this integral as the integral of 1/4 of u, because that's what u is, to the 4th, du, because all of this becomes my du. I can pull the 1/4 out front, and this becomes a very easy integral. I can use power rule for this polynomial. The 1/4 is my coefficient that stays along, and this, when I raise it, it becomes u to the 5th times 1/5. And in this case, this is an indefinite integral. I don't have bounds, so I have to remember to add a constant. In my final step, I can multiply a 4th times a 5th and get a 20th. U to the 5th plus c. The next problem, so these are the problems that we're going to talk about. The next problem I want to talk about is 5.5, number 5. And this is a definite integral that's going to be very similar. And one of the big questions when doing u-sub integrals is which thing do I want my u to be? And to a certain degree, it's just something that you can learn through practice or through trial and error. Let's say that I pick one of these things to be my u, and if it doesn't work out, well, then you try another thing to be your u. In this case, I see that e is raised to a really messy power. So I'm going to set my u equal to that messy power, which is negative x to the 14th. That means that my du is going to be equal to negative 14x to the 13th dx, which is fortunate because I have an x to the 13th here that I can use as part of my u-sub. Again, I don't have the negative 14 coefficient, so I'm going to do the same trick that I did before. I'm going to multiply by negative 1/14 and negative 14. This doesn't change the value of the integral at all because I'm just multiplying by 1. X to the 13th, e to the negative x to the 14th dx, and I have all of my pieces for my du. I'm going to use the negative 14 and x to the 13th, and the dx all become my du. I'm going to pull this coefficient out front. Oh, one other thing. I'm going to do this in a slightly different way than one of the examples. My x bounds go from 0 to 1, and I'm going to leave them in terms of x. This is sort of an abusive notation. So if some other mathematician comes and haunts you, tell them that I told you that you could do this abusive notation where I'm keeping my bounds in terms of x, writing x equals 0 here to remind myself of that, even though the inside I'm going to convert into u's. So this becomes e to the u, and all of these other underlined pieces form my du. I think this is a step that people commonly forget when doing u substitutions. The whole point of doing this is to make easy integration. And by that I mean don't forget to integrate. Because sometimes we go through all of this process of plugging in these u's and then people don't actually take the step of integration. So the constant goes along for the ride. That's one of our rules of constant multiples for integration. The integral of e to the u in this case is just e to the u, and I'm going to evaluate it as x goes from 0 to 1. So I can't plug this x in for u because I need to make sure that this is rewritten in terms of x. So I get negative 1/14 e to the, what is u? U is actually equal to negative x to the 14th, and now I can evaluate it as x goes from 0 to 1. So that becomes negative 1/14 when I plug in 1. 1 to the 14th is just 1, so I get e to the negative 1 minus negative 1/14 e 0 to the 14th is just 0, negative 0 is 0, so I get e to the 0, which is actually equal to 1. Recall that negative exponents are the same thing as dividing by or multiplying by the reciprocal, so I get negative 1 divided by 14 is this first term. The minus the negative becomes a plus. E to the 0 is just 1. So this becomes my final answer. And I could rewrite this with a common denominator, or I could plug it into a calculator to get a decimal approximation. Let's look at 5.5, number 11. Again, the important thing in this section is to figure out what do I want my u to be when I'm trying to do a u sub. In this case, I see that the sign is the outside function, and so natural log of 13x is going to be my inside function. And I'll set u equal to the natural log of 13x. Oh, this might be where the problem is coming in. This is, what is the derivative of the natural log of 13x?